Hello and welcome back to eTech Video Production. This video segment is part 1 of 6 on Cisco EIGRP. Segment 1 is the fundamental of EIGRP. Here we'll go over what is EIGRP, why the development of EIGRP was necessary, and what makes it special over other dynamic routing protocol. We'll follow up with enable EIGRP through a lab, and finally, how does EIGRP works in detail. So we begin with what is EIGRP. EIGRP stands for Enhanced Interior Gateway Routing Protocol. It is a dynamic routing protocol developed by Cisco, used to exchange routing table with its neighbor as long as they are within the same autonomous system. Autonomous system is a number that represents a collection of systems or devices that fall under one administrative entity or a domain. In EIGRP case, all devices running EIGRP protocol, they must be in the same autonomous system before dynamically sharing their routing table. It is primarily used as an Interior Gateway Protocol or IGP, and was developed to overcome the shortcoming of Cisco's first dynamic routing protocol, EIGRP. The following table was prepared allowing us to compare EIGRP to other dynamic routing protocols. In this table, I have excluded the two-link state routing protocol, or SPF, and intermediate system to intermediate system, as we'll compare those with EIGRP on another video segment. But in this table, I have included RIP version 1 and EIGRP. Even though they are deprecated, they are included here so we can see why the development of RIP version 2 and EIGRP was necessary. Starting on this table is the standard. Both RIP version 1 and RIP version 2 are open standard, while EIGRP is Cisco proprietary. Cisco developed EIGRP in 1992 to overcome the shortcoming of EIGRP. However, it is also Cisco proprietary. But in the year 2013, Cisco released it to public, and in 2016, it was published in the RFC 7868 as an open standard routing protocol. Speaking of protocol that is next on our list, all three of these routing protocol is classified as distant vector. Distant vector routing protocol use distance to calculate the shortest path to the remote network, which they call metrics, and that distance for RIP version 1 and RIP version 2 is hop counts. Hop counts is the number of routers I have to hop through before I can get to my final network destination. Both RIPs have a maximum hop of 15, therefore they are unsuitable for a smaller organization. EIGRP is also a distant vector routing protocol, but their distance is composed of 5 vector metrics, which is bandwidth, load, delay, reliability, and MTU. They feed all these 5 vector metrics in a complex mathematical formula to compute for the lowest metrics. EIGRP is also classified as a distant vector, but Cisco has imported many of the link state routing protocol components into it, so Cisco call it Advanced Distant Vector Routing Protocol. We'll cover more of this Advanced Distant Vector Routing Protocol in the second half of this video. EIGRP was developed back in the mid-80s, where bandwidth is in the kilobits to maximum of tens of megabit per second, but by 1990s bandwidth has risen in the 10 megabits per second to hundreds of megabit per second. And this is one of EIGRP's shortcomings. It just could not tell the difference between interface that was in that high of a bandwidth. So when Cisco developed EIGRP, they used a new formula. It's called diffusion update algorithm. This duo takes the same vector matrix from EIGRP and multiply that by 256. This multiplication allows EIGRP to tell the difference between high bandwidth up to 10 gigabit per second. And that was okay in the 90s or the 2000s, but from 2010 on, bandwidth began to rise in the hundreds of gigabit per second, and soon it's going to be in the terabyte per second. So the EIGRP that developed in 1992 is now referred as Classic Mode EIGRP, where Cisco has developed a new one. They call it the Name Mode. We'll go through Name Mode EIGRP more detail in video segment 5 and 6. Because of the distant vector inheritance, EIGRP same as EIGRP, they have a maximum hops of 100 hops, where they can change it to 255, so EIGRP is suitable more for medium to larger organization. And next on our table is the administrative distance. Administrative distance is a number that represents the trustworthiness of a routing protocol advertisement. The lower the number, the more trustworthiness of that advertisement. In Cisco device, EIGRP have a number of 90. Next is EIGRP of 110, followed by RIPS at 120. If your Cisco device is running both RIP version 2 and EIGRP, of course it's going to trust EIGRP over RIP version 2. Next is router tables. Because of true distant vector, RIP version 1, EIGRP, and RIP version 2 can only have routing table. Where EIGRP, with the use of that advanced distant vector, it allows it to build 3 tables. A neighbor table, a topology table, and last is routing table. More on these tables coming up shortly. The last 3 things on this table is some of the reason why RIP version 1 and EIGRP was deprecated. And we start with route advertise. Route advertise is a process where a router sends its routed information to its neighbor. RIP version 1 and EIGRP will broadcast that information to its neighbor at a specific interval. The broadcast and its interval cause 2 major problems. The first is this constant broadcast. Whether your network has any change in the last 6 months, at every 30 seconds or 90 seconds, these routing protocol will broadcast to all neighbors whether they like it or not. The second is the slow conversion. Imagine if you have a router 1 here connecting to router 2, where router 2 is connecting to router 3 and so on. When a new network has just come up on router 1, it depends on when did it come up. If it come up just right after router 1 has already advertised to router 2, it have to wait for the next 20 plus seconds before it can update router 2. And the same from router 2, it might have to wait that 20 plus seconds before it's sent to router 3. So imagine if you have 10 hops away, it could take up to 3 minutes before your entire network know about this new network X. RIP version 2 still inherit that constant update at every 30 seconds, but they do it a little bit better by the term multicast. Multicast allow neighbors to want to receive that information or not, where broadcast they don't have a choice. RIP version 2 broadcasts at 224.0.0.9, where EIGRP will multicast also at 224.0.0.10. The difference between EIGRP and these routing protocol is they only send updates when there is an actual change in the network or topology, and that is called trigger updates. The next on the list is variable length subnet mask, or the capability to do classless networking. Both RIP version 1 and EIGRP does not support that, where RIP version 2 and EIGRP do support variable length subnet mask. And last on our list is authentication. Authentication process on a router is its capability to validate its neighbor before sending out its routed information updates. RIP version 1 and EIGRP do not support authentication, where RIP version 2 and EIGRP do support authentication per interface. The following lab was built to allow us to configure EIGRP, see its operation, and manipulate it throughout all 6 video segments. So let's do a quick review of its topology. Starting with the core, it is a layer 3 switch with IP routing enabled. It has 4 VLANs, 172.16.0, 172.16.1, 172.16.2, and 172.16.3/24 subnet. Upstream of the core switch is router 0. Router 0 is connecting in a partial mesh with router 1, router 2, and router 3. Each router on gigabit 03 is a PC to simulate a LAN on 192.168, followed by the number of the router respectively. Then upstream of router 3 is the firewall, where it has full connectivity to the internet. The firewall is nothing more than a Cisco router, but it's running something called zone-based firewall. Zone-based firewall is the fundamental of all firewall, no matter what manufacturer. So if you are also starting into security, or simply just want to know how firewall works, please subscribe to our video channel and search for Sean's video on zone-based firewall. Let's go over the step of enabling EIGRP. There are 3 basic steps in enabling EIGRP. Once in the global configuration, the first step is enabling EIGRP with the command router EIGRP followed by an autonomous system number. Again, autonomous system is just a number that represents your entire entity or domain. You can choose the number between 1 to 65,535 or 2 to the 16. The second step is the network command to choose which network you want to participate in EIGRP, followed by the network ID of an interface. You have an option to include the wildcard mask or inverse mask. We'll discuss that in part 2, the advanced configuration of EIGRP. But for this lab, I want to keep it simple by just choosing the network ID. Let's start with router 2. Router 2 have a LAN followed by 2 interconnecting interface. First, EIGRP will take a look at the first octet, and that is 192. EIGRP will know this is a class C, so you must enter the second and the third octet. In our case here, 192.168.2.0. Next is the 2 network that point into router 0 and router 3. We also want to enable those so we can become adjacent with them. So network and both of these networks are on the 10 network. EIGRP will look at it. That is a class A. So you only have to type in 10.0.0.0. Let's do one more on the core switch. The core switch have the upstream of 10.0 network. So all we have to do is net 10.0.0.0 and follow up with all the VLAN subnet by net but all the VLAN begin with 172. That is a class B, so we must enter 2 octet 172.16 followed by 0.0. And finally, the third step, no auto-summary. Prior to iOS version 15, by default, all Cisco devices will summary under EIGRP. What that means is it will summarize all the class lists. For example, 172.16.0.0/24 here. It will summarize it back to 172.16.0.0/16. And the 172.16.3.0/24 here, since the first octet is a class B, it will also summarize it to 172.16.0.0/24. This auto summary is useful if all your network is in a classful network, but if they are in a classless network, it can cause major problem. Here's a quick explanation of that. I have router 1 here. Behind router 1 is the LAN with 172.16.5.0/24 network. And router 2, its LAN is 172.16.100.0/24 network. Upstream of both router 1 and router 2 is router 3. With auto summary turned on, router 1 will send router 3 a summary address of its network, and that is 172.16.0.0/16. And also router 2 will send router 3, I also have 172.16.0.0/16. Router 3 will then put both paths to reach 172.16.0.0/16 network in its routing table and will load balance. This will cause a major problem if somebody in behind router 3 trying to go to 172.16.100.72. Router 3 would then load balance out of both interface toward router 1 and router 2, as it will lose 50% of its packets. And this is the reason why you need to turn off auto summary with the command no auto summary when your network is in a classless or variable length subnet mask subnet. Starting with iOS version 15 and above, Cisco turned off auto summary by default. All the routers that we are using for this lab is running version 15.6, so this command not even necessary for our lab. Now you have the basic understanding of our topology and the configuration step for EIGRP. Let's dive in and enable EIGRP on our routers. In this lab, I will use autonomous system number 10, and I have also enabled EIGRP on router 2, router 3, and the firewall. So we need to enable EIGRP on the core switch, router 0, and router 1. Our lab was built on EIGRP Network Simulator. EIGRP Network Simulator is a product of a company out of London, UK. Throughout the years, I have used so many network simulators, such as Cisco Packet Tracer, Boson NetSim, GNS3 to Cisco Viral. And in my opinion, not putting down other network simulator, I found EIGRP to be the most friendly and responsive. We do have a few videos on installing and set up EIGRP Network Simulator, so please subscribe to our channel and look for them. We'll start first with router 1. Let's see what the routing table look like. Show IP route. And only local connected network there. Let's see if it's running any dynamic routing protocol. by show IP protocol, and it does not accept for NSF. NSF stands for non-stop forwarding. It is a service on Cisco network device that allows them to find any alternative path to continue routing as their primary path failed. And let's start with configure EIGRP on router 1. Let's go to the privilege mode followed by the global configuration mode. We'll turn on EIGRP with the command router EIGRP, and you can see here autonomous system number can be between 1 to 65,535, or you can actually use a name. They call it name mode EIGRP. We'll cover that in part 5 and 6 of our video segment on Cisco EIGRP. Here we choose autonomous system number 10. We'll start first with the LAN network of network 192.168.1.0, then followed by network 10.0.0.0, which cover both gigabit 0 and gigabit 01. And we have a neighbor with router 3. Let's take a look at the messages. Diffusion update algorithm exchange EIGRP for IPv4 on autonomous system number 10. The neighbor is 10.0014, which is our 3 gigabit 01 interface. And our exiting interface is gigabit 01, and the adjacency is up. Currently, router 0 is not running EIGRP, so router 1 does not have any adjacency with router 0. Let's continue with the core switch. Again, let's see if it's running any dynamic routing protocol. Show IP protocol. And it is not except for non-stop forwarding. So let's go to global configuration mode, router EIGRP 10. This time we'll start with the interconnected network first by network 10.0.0.0. Now for all the VLANs. Since they begin with 172, that is a class B, so all we have to do is network first octet followed by the second octet. And you see here it does not have any adjacency due to router 0 again not running EIGRP. So let's go to router 0. Here in router 0 again show IP protocol, and there is none, so let's configure EIGRP. Autonomous system 10. We'll start with the LAN 192.168.0.0 and followed by the 10 network. As soon as I hit enter here, we should have 3 neighbors, the core, router 1 and router 2. And there is the 3 messages of new adjacency. The 10.00.1 is the core switch, the 10.006 is router 1, and 10.0010 is router 2. And you can see how easy it is to enable EIGRP on Cisco device. So how does EIGRP works? The first is Protocol Dependent Module, or PDM for short. PDMs is responsible for many things, including maintain EIGRP neighbor and topology tables, implement filtering and summarization of routes, redistribution of EIGRP to and from other routing protocols, and translate those information to diffusion update algorithm for their metric calculation. More on the PDMs in the deep dive into EIGRP. Next is the neighbor discovery. It is used to dynamically find other routers running EIGRP and perform adjacency, followed by diffusion update algorithm state machine. The primary function of DUO is to calculate the best path, but must be loop-free to all remote networks in the autonomous system. And finally, the Reliable Transport Protocol, or RTP. EIGRP utilizes RTP for the guaranteed delivery of EIGRP packets. These four components all work together to create the heart of EIGRP, the EIGRP tables. And first on its list, the neighbor table. The neighbor table contains a list of all adjacency EIGRP routers. EIGRP uses this neighbor table to maintain neighbor relationship, send in routing information update, and from those routing information update, they help build the next table, the topology table. The topology table is where EIGRP contains all directly connected networks and all remote networks learned from the neighbors. Once this table is built, EIGRP will then use the diffusion update algorithm to calculate the best path to a remote network, which is called the successor, and if possible, a second path, which is called the feasible successor or a backup route. And from there, EIGRP will copy all the successor to the next table, the routing table. And just like any other routing protocol, routing tables are used to route or forward packets to remote networks. Let's review the hellos and the updates between router 0 and router 1. Router 0 starts by sending hello to router 1. Inside the hello is autonomous system, dead time, and a K-value. Router 1 will look at the hello, and there's two requirements to establish adjacency. The autonomous system number must match, as well as the K-values. If they do match, router 1 will immediately send back its update. In this update, it contains all routing information from router 1, and also router 1 will send a hello back to router 0. As we mentioned it before, EIGRP uses Real-Time Transport Protocol, or RTP, to guarantee the delivery of all EIGRP packets. So when router 0 receives the routing information update from router 1, it must send back an acknowledgement to router 1. Router 0 also have a chance to review the hellos from router 1 with the autonomous system and a K-value match. It will send back its routing information update. And last, since this is a routing information update, router 1 will send back an acknowledgement. Routing information updates are typically exchanged in the initial adjacency establishment. Once all these routing information updates has completed, EIGRP will complete the building of its topology table and routing table. From there, they will put all these remote networks in the passive state, as they only send hello as a keep alive. These hello do not require an acknowledgement. Therefore, in these hello, they do include a dead time value. The dead time is the amount of time. If you don't receive a hello from me past that dead time value, you had just lost a neighbor. Again, if I have failed to mention before, the default value for hello is 5 seconds, where the dead time is 3 times the hello, or 15 seconds. The only other types of exchange between neighbors are lost route and stuck in active query. I will cover those in the video segment 4 and 5, the deep dive of EIGRP. Let's examine the hellos and routing updates between router 0 and router 1. Currently, all routers are running EIGRP, so I'm going to log into router 1 and shut down the interface pointing to router 0. Interface gigabit 0/0 and shut down. We should see a message of lost a neighbor right there, and the interface is down. and EIGRP do exchange is down. So next we'll go to router 0, and let's just see show IP EIGRP neighbor, and we only have 2 neighbors left. 10.001 is the core switch, and 10.0.0.10 is router 2. As of right now, router 0 is still sending hello out of gigabit 01. So let's capture gigabit 01 and examine what is being sent out. And we see hello. Let's stop the caption here, and you can see the hello are sent out at every 5 seconds. Let's examine the hello in a little bit more detail. We open up the hello right here, Cisco EIGRP, and let's put this down so we can see more detail. And let's take a look at the parameters as well. And you can see these are hellos, autonomous system number, and here's all the parameters for the K-value. Now let's re-enable the interface gigabit 00 on router 1. Before we do that, let's capture all packets leaving interface gigabit 0 on router 1. And you can see it's still receiving hello from router 0. Let's re-enable interface on router 1 by no shut. And 1 came up, the 2 came up, and do exchange happen. And you can see these highlight in red. Let's stop and review the statistic. And you can see here is router 10.006, which is R1, is sending hello, and immediately we have a router updates. Here I highlight in blue is the routing updates from router 0, and here is all the routing information on router 0 sending to router 1. Next are these acknowledgement right here. Since router 0 is send those routing update, router 1 is reply with an acknowledgement. Then here is the update from router 1 and the acknowledge from router 0. Let's take a closer look at EIGRP neighbor table. Here I am on router 1, so we begin with show IP EIGRP neighbors. And we have 2 neighbors on router 1. The first neighbor is 10.0.0.5, which is router 0. The second is .14, which is router 3. The interface here is my local interface, which is connecting to that neighbor. The whole time represent how long in second before those neighbors become invalid. As you remember, EIGRP will send hello every 5 seconds. Once the hello is received, the whole time right here will be reset to 15 seconds and begin to count down. In normal operation, you will never see this number go below 10 as they've been reset by the hello at every 5 seconds. Uptime is how long I have been adjacency with my neighbor. As you can see, I only been up neighbor with router 0 in the last 3 and so minutes due to I shut down the interface and bring it back up earlier. Prior diving too deep in the topology table, I'd like to go over the EIGRP metric calculation formula. And that metric calculation is this complex formula here. To behave like link state routing protocol, EIGRP use variables such as bandwidth, load, delay, and reliability, but those variables can be activated or deactivated with the K-value, and I have a table here so we can go over them. First on the table is K1, represent the bandwidth, and EIGRP will use the lowest bandwidth along all links. Here's a quick example. Router 1 is connecting to router 2, connecting to router 3. The link between router 1 and 2 is 10 gigabit per second, and the link between router 2 and 3 is 1 gigabit per second. The metric will only use 1 gig per second. Next is K2, which is the worst load on that link, followed by K3, which is the delay. In the delay is the sum of all delays. The link between router 1 and router 2 is 10 microsecond, where the link between router 2 and router 3 is 30 microsecond. The sum is now 40 microsecond. Next on the list is K4, which is the reliability and is the worst reliability of a link. K5 represents the MTU of a link, which is the smallest MTU of each link. And last on the table is extended attributes, which is used for scaling for bandwidth above 10 gigabit per second. K6 only in use when we use name mode EIGRP, so for our lab, K6 is not in play. So where does EIGRP get these attributes from? It is actually on the interface itself. I have a capture here on router 1 on gigabit 03, so let's take a look at them. Here is the bandwidth of 1 gigabit per second or 10 to the 6, followed by the delay of 10 microsecond. The reliability here displays 255 over 255, which is 100% reliable, where the transmission load and the receiving load is 1 over 255, which represents 0, and finally the MTU at 1500 bytes. Let's clean this up so we can continue with the default value. By default, the EIGRP on Cisco device have K1 and K3 as 1, where everything else is 0. So let's go back to this calculation to see which one is actually in use. K1 is 1, so this is in use. K2 is 0, and any number divided by 0 is considered undefined. Therefore, this is not in play. K3 is equal to 1, so the delay is in use. And K4 and K5 are 0, therefore they are not in use. So now the formula actually looks like this. The final metric calculation have 256 times 10 to the 7 or 10 gig divided by minimum bandwidth plus the sum of all delay. To be able to use load or reliability, you have to turn this K-value on. And remember, if you turn on a K-value of an interface, your other neighbor also must match that K-value as well. Many people ask me if they want to turn on this MTU or K5, where is the MTU actually fit in? If you look at the original formula here, MTU is actually not in there. So I have no idea how to implement MTU. Over the year, I heard one person said the MTU are used when you have load balancing and you want to vary the MTU. Again, there is no place for you to fit that 1500 by MTU in this formula. I think whoever invented this metric calculation here drank one too many of those glass with a worm inside during their development. Now we have our final metric calculation. Let's head on over to our lab and perform a few metric calculation. Me personally, I think whoever developed this metric calculation here and during their development they drank one too many glass that had that little white worm inside. Anyway, back to the metric calculation here. Now we have a simplified version of the EIGRP metrics. Let's head on over to our topology so we can perform a few metric calculation. My ultimate goal in this metric calculation is to figure out from router 0 what is the total cost to get to this remote network. So we have to begin with router 1 and what is the cost for it to get to the LAN. Since this is a gigabit interface, so that is 10 to the 6 as the minimum bandwidth. Followed by, we need to get the sum of all delay, and since this is the only interface, we'll find out what is that interface delay is. I'm here in router 1, so show interface gigabit 03, and you can see here the delay is 10 microseconds. So let's put that into our formula. We have a 10 here, so let's rewrite this equal to 256 multiplied by 10 to the 7 divided by 10 to the 6, which is 10, plus 10 divided by 10, which is 1. So 256 multiplied by 11, which is equal to 2816. Let's log back into router 1 to see if that number is true. So with the command show IP EIGRP topology, highlight here is the output for 192.168.1.0 is directly connected on my gigabit 03, and my cost or the feasible distance is 2816 as we just calculated. Now router 1 will advertise to router 0. I have a way to get to 192.168.1.0 and my cost is 2816. Now all router 0 need to do is figure out his interface cost and add it to that 2816. So let's write this and calculate the cost from router 0 to router 1 for that network. Again, router 1 is advertised a cost of 2816. Since both interfaces are in gigabit, so this is no longer in play. And the delay is the same as gigabit 03 on router 1, so that is a value of 1. So 256 multiplied by 1 is equal to 256. So router 0 will add 256 to that total cost. So the final number should be 3072. So let's log into router 0 to verify that number. Here in router 0, show IP EIGRP topology. The highlight is the output from router 0 for 192.168.1.0, where it had one successor and the feasible distance is 3072 via 10.006, which is router 1. The number in the back is the advertised distance from router 1, where the number in front is the feasible distance. Let's take a look at more detail about this network in the topology table. And the command is show IP EIGRP topology for 192.168.1.0. First, the topology is for autonomous system number 10 for the 192.168.1.0. The state for this network is passive. One successor, the feasible distance is 3072. I have learned that from 10.00.6, and here is all my vector metrics. And the router that sent me that information is router ID is here. Now you can see the calculation for the metric for EIGRP is not too shabby. Now let's head on over to the topology table where we take a look at detail how router 0 built its entire topology table. And last on our video segment is the topology table. Here I will be focused on router 0 and the 192.168.1.0 and 3.0. First, let's focus on 192.168.1.0/24, and router 0 learned that from router 1 at 10.0.0.6. First, the advertised distance. Router 1 will advertise 2816 to router 0. Router 0 will take this 256 and add to that 2816, and the feasible distance is 3072. Router 2 also advertised to router 0, so we have 10.0.0.10, composite matrix of. Starting from router 1, router 1 will advertise to router 3. He have a cost of 2816. Router 3 will take this 256 and add to that and advertise as 3072 to router 2. Router 2 then take this 256 and add to that 3072. Then finally advertise to router 0. My total cost is 3328. So that number goes here. Router 0 will then add this 256 to that number, and the final number is 3584. Let's redo that with the network of 192.168.3.0/24, and it also learned that network from 10.0.0.6, which is router 1, and 10.0.0.10, which is router 2. Let's clear this up. For the 192.168.3.0, router 3 will advertise both to router 1 and router 2. His cost is 2816. Router 1 will then take this 256, add to that 2816, and advertise to router 0 at 3072. Same thing for router 2. He will take his 256, add to that number, and the number is 3072. So the number back here is 3072. Router 0 will then take the 256 here and add to the advertise of router 1, and the number is 3328. Same thing from router 2. Router 0 take 256, add to this advertised distance, and the number is 3328. Next, router 0 will find which is the fastest way to get to the remote networks. With the 1.0, this is its lowest number, so this is the feasible distance, and that network will be copied to the routing table. For the 3.0 network, both costs is the same, therefore both of them are feasible distance. Now router 0 have two successors, and both of these paths will be copied to routing table. Now what about this path? Could that be our feasible successor or a backup route? But not so fast. For a path to become a feasible successor, there is a condition, and the condition is the advertised distance for that path must be less than the feasible distance of the best path. Let's re-examine this path. the advertised distance of this path, which is this number here, it must be less than the feasible distance, which is this number. In our example here, it is not. Due to afraid of this path can cause a loop in the remote network, EIGRP will completely remove this path from its topology table. Therefore, this path is not qualified as a feasible successor or a backup path for this network. In this particular example, we don't have a feasible successor, but on our next video segment on the advanced EIGRP, there will be feasible successor there. So you can check that out on the advanced video segment of EIGRP. Let's verify the topology table on router 0. We'll start by look at the topology table of router 0. Here is 192.168.3.0. The feasible distance is 3328. Both paths have the feasible distance of 3328. Therefore, I have two successors. Now let's take a look at 192.168.1.0. It only has one successor, 3072 via 10.6, which is router 1 out of gigabit 01. Let's take a look at the detail for show IP EIGRP topology for 192.168.1.0. One successor with a feasible distance of 3072. Now let's take a look at the 3.0. Two successor, 1 to 10.006 and 1 to 10.0010. And finally, let's take a look at the routing table. For the 1.0, only one path with a cost of 3072. And for 192.168.3.0, I am load balancing across since they both have the same feasible distance. And that is how EIGRP builds its routing table. And last on this video segment I'd like to cover is the main feature of EIGRP. And first on this list is support for multiple autonomous systems on a single router. What that means is if your organization is currently running autonomous system 10, they're going to purchase or partner with another organization and they are currently running autonomous system 20, you can put a router in the middle where one interface on AS10, another interface on AS20, and perform something called redistribution. Redistribution allows all networks from Autonomous System 10 to be sent over to Autonomous System 20 and vice versa. We will cover redistribution in video segment 2, the advanced configuration of EIGRP. Next on the list, a few years after the development of EIGRP, Cisco has adopted the Classless Network Service, or CLNS. This allowed them to support IPv4, IPv6, Novell NetWare, or IPX-SPX, and AppleTalk. We went over the Protocol Dependent Module, or PDM. PDM allows Cisco EIGRP router to communicate and send EIGRP packets reliable via RTP. Next is diffusion update algorithm. It allows EIGRP routers to calculate the best path for all remote networks. Also allow EIGRP to build neighbor, topology, and routing tables with backup routes, or they call it feasible successor. And last on this list, load balance over unequal cost paths. This is a very unique feature about EIGRP Dynamic Routing Protocol, and we will cover them in video segment 3, the deep dive of EIGRP. I know this has been a long video, and I do want to thank you for watching this video. I hope it was intuitive as much as informative, and if you like this video, please click that like button below and subscribe to our video channel, as you can see more video on EIGRP as well as other technologies. Till then, stay safe, and I'll see you in segment 2, the advanced configuration of EIGRP.